Hello everyone, welcome back to a new episode of Advent of Code. We are going to do day 7 today, so let's get started. I said 7, but the number on the screen is 8, and that number is the correct one. Okay, day 8, memory maneuver. The sleigh is much easier to pull than you'd expect for something its weight. Unfortunately, neither you nor the elves know which way the North Pole is from here. I mean, north, right? Is that where today's joke is? No, apparently not. Okay. You check your wrist device for anything that might help. It seems to have some kind of navigation system. Activating the navigation system produces more bad news. Failed to start navigation system. Could not read software license file. A classic. The navigation system's license file consists of a list of numbers, your puzzle input. The numbers define a data structure which, when processed, produces some kind of tree which can be used to calculate the license number. The tree is made up of nodes. A single outermost node forms the root, and it contains all other nodes in the tree, recursively. Specifically, a node consists of a header, which is always two numbers, the quantity of child nodes, and the quantity of metadata entries. And then 0 or more child nodes, as specified in the header, and 1 or more metadata nodes. Each child node is itself a node that has its own header, child nodes, and metadata. Okay. I see. So they've drawn a thing here. So this means our first node has 2 children. No. The header is always 2 numbers. Number of children, then number of metadata. So it has 2 children and 3 metadata entries. Okay. And I don't yet know, like, exactly how the rest of this... So it has 2 child nodes, B and C. I see. And so the metadata entries come after the children, I guess? Where does it tell me that? Like, if I couldn't read this, wouldn't I be in quite a bit of trouble? Because I don't see here where it says, like, what the format of the actual tree is. I mean, it's easy to figure out from reading this, but usually the text is very explicit about everything that matters. And here, it seems to me like the only way you can understand the layout of child and metadata entries is by looking at this graph. Not graph, it's a diagram, right? So, like, for example, someone who is blind and is doing this puzzle would be in more trouble than usual, given that Advent of Code is usually pretty careful. But okay, fine. This seems pretty straightforward, I think. So B has 0 children and 3 metadata entries. The next 3 are its metadata entries. Fine. And then C. So this is actually an excellent candidate for parsec, I think. We can have our tokens be... Well, I guess we might as well start with characters, but we could actually have, you know, we could have a parser of whose input format is whose input token is an int rather than a character, and parsec would be perfectly happy with that as well. But we could also just like rebuild. We could build up. We could do the obvious thing and like have parsec handle everything rather than having some input processing and then parsec. Let's just do it all in parsec. So it should be pretty straightforward. So we first want a data node is a node of, well, it has a list of metadata, which is a list of int. And you know what? Let's say a node of A. We can be more I don't know. Oh, hang on. Is it? Yeah, this is fine. I was thinking we might need multiple constructors and then we shouldn't really use a record, but this tree controls its branching factor by how long the lists are, not by like using some different constructor like a leaf or a branch node. Everything is a branch, it just might have no children. And in addition to metadata, we have a list of children, which is a list of node of A. Yes? Seems good. Let's derive show on this, because we might want to print it. And so what we want is a parser for node of int, right? Although, to be honest, we could write a parser for anything that's readable, right? Couldn't we? I think so. I think it'd be a little more general. But okay, let's go get parsec again. So this is not something, for example, that we would use regex applicative for. This is a more complicated input format than can be. It's recursive. Like you kind of need a Turing machine to handle it. Applicatives, well, regexes. Do you need a Turing machine? Maybe not. But you do need more than an applicative. You need monad because the structure depends on the values. When the structure is fixed, you can use an applicative. But when you need to know what values are in the string to determine the structure of the output, you typically need a monad. And applicative is not strong enough. So what we want... God, what's another day where we used parsec? Because I, don't remember what's useful to import. All right, let's just, take most of this stuff. Wow, what is this? It's like a temp Haskell file that it built from something? But okay, whatever. So we want, some of this stuff, and that's probably plenty, right? Spaces, digit, char. Yep, those all seem good. Parse, many one, parse error. Those all seem good, although it turned out I don't really need parse error. Because we were using, we used traverse to kind of handle that. Okay, so what I want is node is a parser for node. I don't know. Let's just get rid of this stupid being more general is kind of, it's a virtue in a way, but it requires. It makes type inference a little bit harder. In particular, if you are general enough about the type, and that's great for clients of your library, for example, because they can use it in more than one way. However, they have to specify in which way they use it. Usually that's fine because they're using it in some context where the types can be inferred and they don't even have to do any work. But when our only client is main and we just kind of call some all we would have to do is we would just be adding more type annotations for no particular reason. So I'm just not going to bother. So node is a parser for node. And let's also define int as a parser for int. And int is read many one of digit, right? Yes. So node is something like this. Node equals do. Num children is an int. And then I want entero mode on, and I didn't do that yet. And it would have complained if I had an uncompilable source file, so I just threw an undefined in there for a minute. So if I load this, parse is incorrect. Sure. Traverse node, is that all? No, it's parse. What is the type of parse, please? Yeah, very funny. Undefined, whatever. Please compile my file, and then now it knows what type parse should have, right? parse takes a parser and returns a string? What? Oh, it's inferred that from context. Ugh. So, like, what I really just want is, like, what is the type of parse, please? That's the real type of parse. So it wants parse. It wants a parser, so that's node. And then it wants a file name, which is standard in. And so what's the deal here? Part 1 takes an input. Either... Ah, right. I always forget you have to put this fmap here. Could match type node with list of node. That's weird. I don't want to traverse because I've been using traverse because I've like been parsing some in previous examples, because I parse something that returns a, maybe a list of thing, and I want a list of maybe thing. But here I just get a parse. I get either an error or a single node, and so I just want to fmap over that. I don't need the traverse step. Okay, fine. So having parsed the node, we have a number of children. And we now need to... Oh, right. Something else I wanted to know, in Taro, please, is where is replicate m? Is that in... it's in control monad, I assume? Yes, great. And now we just want to say children replicate m node of... No, not yet, actually. We want to... spaces. Replicate m node num children. And finally, we need to parse the metadata entries. What is the correct way of doing this? I think I want from here sep by 1. Meta should be sep by 1 spaces of int. And then finally I will return the node of children and meta. What is the type of replicate m? It wants the int first. Okay, well that's one problem. And we want the meta first as well. It has an incorrect type. What's the type of sep by 1? It takes a parser of unit? Why unit? And another parser of int. Oh, I see. Unit, right. The first parser is getting thrown away. Then it takes a parser of int and returns a parser of list of unit. Okay, so I guess I have these backwards. Ah, right, because you're expected to use it like this. Yes. So ints separated by spaces. Got it. So let's just oops, well. So I just want to see if this successfully parses. And to do that, we should be over here. Stack run GHC. I already fetched my input, by the way. I haven't looked at it, but I went and grabbed it earlier. Unexpected end of input, expecting space or digit. Sure. We made a mistake. It should have been sep end by, I believe, right? Let's go look at the docs for these. Haskell sep end by in parsec sep end separated and optionally ended by sep. So it'll parse the spaces in between things, and if it finds another space at the end, it'll consume that and throw it away. Which is perfect. That's what we want. The problem was that, well, I think anyway, the problem was that after we finished parsing, the first leaf node, or hang on, I also forgot a space here, right? Because in between the children and the metadata, there should also be spaces. Okay. How about now? Line 2, column 1, unexpected end of input? I would have expected it to be upset that, like, there was a character left at the end, right? Okay, well, you know what? Like, this is just... all these spaces just make everything worse, right? Why don't we actually do... this? Not lines, but... Well, yeah. So my thinking is to... Wait, why does this compile? What? Oh, it's assuming read is going to have type string to string. It's going to read a bunch of strings, which is not what I want. I want to read them as ints. So I need to change my types a bit here. Also, wait, no, I just completely screwed everything up. Okay, I know what's wrong. Let's put this all back because I think it was actually fine. My problem was I forgot to replicate this as by the number of metadata entries. It just read all the ints. I was like, well, that's everything. So what I want is replicate num... Wait, and I forgot also to, like, num meta int as well. What order are they in the input? Children first, then meta. Okay, so this is right at least. And the child nodes are also first. So really what we should do is replicate spaces this. But not put num children. Like that. And then again, I should say meta is replicate num children of spaces to node. Num int? Why are you upset about this? Not node, but int. Here we go. Jeez. Okay. This is much more reasonable. So we first read... spaces. We read the number of children. We read the number of metadata. And then importantly, we don't consume the space after num meta. This is a big improvement. Then we're guaranteed that there's always a space in front of every child node that we're reading. And so we just consume that first and then parse a node. Then we do the same thing for metadata, parsing ints instead. Okay, so let's try that. Okay, and it parses. We get like a big old list of like, well, not list. We get a tree. And it's like complicated and who knows what, but. So now we can actually compute the input. Oh, I just thought of something that. Wouldn't it be nice if this actually were a, like, if it did have a type parameter, because then we could, like, it would be a functor, we could fmap over it, we could traverse it, it would be amazing, right? Not having a type parameter means like all this kind of fancier stuff does not apply. We can write a recursive function that consumes a node and produces what they want, the sum of all the metadata. So that's very easy. And in fact, let's do it now for a little exercise just to show how easy it is. But I also want to at least look at, like, what if we made this, what if we parameterized this type and did it with, like, because, like, we could just derive foldable and then call sum on it, right? Yeah, that would be pretty cool. So, okay, let's first write metadata sum takes a node and returns an int, right? Actually, we don't even need that. We'll just call it part one, right? Part one of n, we'll call it root, whatever, equals, and in fact, we want to pattern match it right now. Part one node of meta children equals sum meta. Is that correct? Yeah, metadata is just ints, right? So plus sum of map part one of children. Yeah, so there's a number. That's the right answer. Cool. So before we look at part two, let's now do something a bit cooler. Well, actually, let's commit this, right? Git add day 8 part 1. Now, let's make this node of A, and we'll store some A's and have children, which are of type node of A. And now we have a parser for node of int. And like, this will all still run exactly the same, right? We haven't done anything yet. But now what I want is language derive foldable, please. Is that not? What did I type wrong? Well, okay, I'll just let Intero mode tell me. Yes, please add that, please. Yep, do both of those. Derive foldable, derive functor. I thought that's what I wrote. I must have had the punctuation. One of these was wrong, the first or the last one or something. And so now our node is foldable and is a functor, and it's like great. And so we can just say part 1 equals sum, right? Isn't that cool? recognizing when the data types that you are building are instances of a more general idea. If you can, even if you aren't like totally sure like what use that will be, making your types actually support those type classes will generally pay dividends. Here I recognized that we really, like, this was a more general structure where we have a tree of something. And okay, in our input we seem to want it to be a tree of int, but it could be a tree of anything. Maybe it would be useful to add a type parameter. I decided not to do that because it would make things, I thought, more awkward. But really all we had to do was put int here and everything was fine. And in exchange, we got part 1 for free. We can just call sum. Oops. Sum takes anything foldable. Any foldable thing containing numbers of some kind and adds them up. And our data type is foldable and it contains ints. So sum works. GHC is smart enough to... Foldable basically means, is there some way to look at the items in this thing one by one? And GHC can figure out, yeah, there is. First, to look at the items in a node, first look at each item in metadata. Then fold over all of the children, which are also nodes, recursively. And it derives that for you. We could have written it, but why bother? And I don't believe I actually need the functor. Foldable doesn't... I keep doing that. Foldable doesn't require functor, does it? No. Traversable does. Well, it requires applicative, but whatever. We don't need traversable. Okay, cool. So let's just commit this as well. Git commit -m day 8 part 1 use foldable instead. And who knows, maybe this will be useful in part 2. Okay, so let's see what part 2 is all about. The second check is slightly more complicated. You need to find the value of the root node in the example above A. So that's the first node. The value of a node depends on whether it has child nodes. If a node has no child nodes, its value is the sum of its metadata. So the value of node B is, whatever. So for leafs, easy. If a node does have child nodes, then metadata entries become indexes which refer to those child nodes. Metadata entry of 1 refers to the first child node, 2 to the second, 3 to the third, and so on. The value of this node is the sum of the values of the child nodes referenced. Okay, so we need to write a function called value that takes a node. Fine. 0 does not refer to any child node. What does that mean? What should you do if it doesn't refer to a child node? Do you skip it, or... If a referenced child node does not exist, that reference is skipped. Got it. Uh-huh. All right, well, simple enough. I mean, I understand the problem. I'm not sure yet exactly what all Haskell things I will use to implement my solution, but... so by the way, something that we could have done, and that I considered, but didn't do, was these 3 lines could have been written in applicative style because none of them depend on each other. They depend on previous lines, numchildren and nummeta. So I could have written, and I think it would turn out pretty ugly, but let's see. We could have written node of this and this, right? Is this better? Excuse me? Did I get these in the wrong order? No. Why is this incorrect? The second argument... Why? Couldn't match type. We run replicate m num children. We run replicate m num meta. And then we call node on the result of those two things. I don't totally understand what types it's saying it can't match. Like, clearly it can't match int with node of int. But why do we have a node of int? That's what baffles me. Replicate m. So, I mean, okay, first thing to point out is that it's implicitly parenthesized in this way, and so there's really no way I can be wrong about the... That wasn't the problem, right? But I just want to point out to you guys that this is how it's parenthesized, so you don't need to worry about any weird stuff like that. So why does it think replicate m... takes an int and a parser of int and returns a parser for list of int, which is correct, and that's what I want. And so, okay, it says I thought you would have a parser for list of node of int, which is like fucking crazy. Why would you think that's what I meant? The actual type is parser of int, which is the only thing that makes any sense. So what am I getting wrong here? Node, oh, do I have the... I did get the arguments in the wrong order. I forgot. I left this in the order I was parsing them. I see. So to do this, if I wanted to write this, well, okay, there you go. Ta-da! Flip node. It would probably have been maybe better to just make node take its arguments in the other order, the order that they appear in the file. Yeah, that would make more sense. I'd have to then change, like... Oh, I never pattern match on node, so that's fine. So let's actually just fix this. This is like, I don't know, it's a bit weird because I kind of feel like the children kind of like, they're physically before the metadata in the file, but I feel like the metadata belongs as being attached to the node and then the children. That's kind of how you typically draw trees. Okay, so we could have written it like this. I don't know that this is actually better. But it's kind of cool, isn't it? I don't know. I'll leave it in. Day 8, part 1, applicative style parsing. How are we for time, by the way? It doesn't super matter, but I'm just... Oh, that was actually pretty fast. I thought by now I would have spent more time. Even though, like, everything that we did is pretty simple, I spent a lot of time on it. I thought. Fine. Now we need a function called value. Value, that's the French value, as you well know. Takes a node of... Well, I mean, int is the obvious thing, but can we be more general? It could work for anything... We could make it work for anything monoidal, I guess. But I don't know. That's just like sort of unnecessarily. That's a little perverse, right? Likewise, we can make it work for any number, I guess. But since our only parser is a parser for ints, like I don't really think that's that worthwhile. Value of, which is first the children. So if there are no children, it's very easy. It's just sum m. How can I turn off like, is there a way to turn off autocomplete mode is what I want to know. Like, what are all of my minor modes? How do I find that out? Help mode? Auto composition, column number. Is it auto composition? What is auto composition? Text characters are oh my god, I don't need that, but it's not the problem. Haskell indentation, tooltip. I don't need tooltip, whatever that is. Font lock, fly check, electric indent, auto encryption. I don't know, none of these seem like, maybe it's part of Intero mode? I wish I could figure out how to turn it off, but I haven't tried very hard, so I can't really complain. The value of a node that has actual children equals sum of map. There's a thing I want to look up on Haskell real quick. Haskell. I have a list of A and an int, and I wish to obtain a maybe A from this list. And it's in... No, I don't want this. That gives me back an A. Why? I'm surprised that that's not like in any, like I totally believe it's not in base. What I don't understand is why it's not in any libraries that are included in Haskell. Right? This is like, I would like to look up a thing, and then if it's not there, I get back nothing instead of crashing the program. But okay, I mean, what would it be called this if it existed? Probably. All right, so we can just define that maybe. So yeah. Is there some more, like, I don't know. One thing that sort of is bothering me is that, like, if there are any nodes with a huge number of index entries, like, looking them up is kind of expensive when you use a linked list, which is what Haskell's lists are. And so it might be nice to do something like convert the node's input. Yeah, let's actually do that. That seems way better, is like build a map out of this. And then I can just look things up by index cheaply. Also, like, what's the deal with int map? I know that exists. Haskell int map. It's in containers already, so that's cool. So it exposes data int map, different strictness properties. I mean, data int map strict is like kind of fine with me. And this is like an unnecessary optimization, I assume, because there aren't any nodes that have 1,000 children and 1,000 metadata entries or something. But like, if there were, this might be important. In particular, yeah. So this all behaves pretty much the same as an ordinary map. It's just like it's not parameterized by its key type. and it'll be more efficient. So fine. So I want an int map. So here's the thing that's sort of bothering me is, suppose that I write this function, right? And what's it going to do? The first thing it's going to do is take the list of children and convert that to an int map. And then the metadata is going to say, like, please compute the value of... I see. I was going to say that it might cause us to compute the value of the same child node many times. And if it's expensive to compute the value of a child node, that could be a problem, right? We could solve that a number of ways. First, we could, before actually doing any of the lookups, we could take the metadata list and, like, eliminate duplicates and say, like, have a list of pairs saying, please give me 4 times the value of child node 1, and then we could look up node 1 one time, multiply the result by 4. That seems like kind of a pain. What I think I'll instead do is just compute the value of every child node, regardless of whether it was asked for, and then just look up the value however many times. If there are very large children that are expensive to compute the value for, and we never look at them, then... because of laziness, we won't actually waste any computation. So that would actually be sort of fine. This makes me wonder, though, do I want... What is the deal with the strictness of int map? What is it strict on? Is my question. So, values of type B. Careful to force the values before inserting them into a map. So this would be... if we used this, we would not get the property that we can avoid computing expensive things. So I actually want the lazy one. Import data.int map qualified strict as m. No, I just said I don't want the strict one. Lazy, please. So let's say part 2, I should say. Oh no, we're not doing part 2. Again, we can just like, part 2 is just a function that takes a node and returns an int, and like I don't need a helper function called value, because part 2 is going to be just that helper function in that case. So what we're gonna do is let well, let's let m child values equal let's see, m dot from list with, oh sorry, you guys can't see this, can you? Yeah, you can. Good. I couldn't remember if I remembered to switch windows. Now I want you on this window, of course. From list with. So it takes a... this is not what I need. Yeah, I just need from list, that's all. Okay. So m.from list of well, from list and zip with lists starting at 1 or ints starting at 1 applied to map, oh, actually, map part 2 of C's, right? So if C's is empty, this will just be like the empty map. And C's won't be empty, we already know, so whatever. We map part 2, computing the value of each node. We zip them together so that they have a number, and we use that to insert into the map. Okay, that seems good. Why are you not? There we go. Now, how do I look up a thing in a map and get back a default value if it's not there? Query lookup returns a maybe. This also returns a maybe. What's the difference? It's just an infix version of the same operator. Find with default. Great. That's what I want. So, by the way, what the heck key is this? This is the hotkey that that I use to switch which window I'm showing, and so that's why you often see like this happen. It's because I've just switched like please show them the coding window. So what I really want to do is make this bound to nothing. Global set key keyboard of nil. Wait, is global unset key a thing? It is. Great. Okay, I'll put that in my RC for later, but that's good enough for today. In sum.map find with, well, the argument order is a little bit wrong, isn't it? Like flip find with m dot find with default 0 child values of m. Import qualify, yeah, well, that's just like your opinion, man. Oh, not in this, oh gosh, not in that. No. Turn off Intero mode in the REPL. Yeah, I just wanted to Intero restart, actually. Great, so that all compiles. And we got a number, great. That's the right answer, lovely. So let's go review. Maybe did I finish explaining what's going on? I didn't really. I just sort of typed this stuff out so we built here a map of the values of all of the child nodes that exist. And we did that so that we wouldn't have to worry about recomputing, wasting any effort on a recomputed value. Multiple times computing the value of a child is not something we have to worry about here. And this is maybe a little bit obscure. But the idea is find with default 0 is like almost the function that we want, but we need to partially apply it to a map. We can't just write this because it wants the map as the last argument, not as the second argument. So by flipping this function, we make it take its first and second arguments in the opposite order, which are the second and third arguments of find with default, which, we apply A and then we flip these two and then partially apply the map. And we get back a function from key to A. And we map that function looking up. That function is a thing that gives us a value for a child index. And then we just map that over all of the indexes we want to look up and sum the results. We zipped with integers starting at 1 because that was how the problem was specified. So there you go. Pretty simple. Not a very difficult part 1 or part 2, to be honest. It was fun to have, you know, parsec handle the input like so nicely. And you know, that's the nice thing about the parser combinator libraries is you get back a value. Like, you don't have like a separate step where you like parse the input and then later you run, like, say with regexes, you like, or like you just split it on word or something, on like spaces. And then you get back a list of ints, and then you do something to process the ints, and like, it's just sort of nice to have the thing that consumes your input produce values that are already of the type that you wanted. And applicatives, well, applicatives give you that power, and also sometimes you need monad as well, which here we do. And it was cool also to have a reason to use a parameterized type that simplified part 1. Okay, so let's just commit all this. Yeah, we wanted int map. We implemented part 2. Yep, git commit -m day 8 part 2. Cool. Well, thanks for joining me, everyone. And we're done for today. Thanks for watching, and I'll see you next time.